Let's talk about laws of exponents. So first off, the definition of an exponent. So an exponent, we have a base, which we'll call A, to a power, which we'll call N. But what that notation means is that we're taking that base times itself, however many times the power says. So A to the N is A times A times A times A, whatever, N times. That definition determines all of the rules of how it behaves, along with what has previously been established of how addition, subtraction, multiplication, and division work and with each other. Then this definition of what the exponent means determines how it works. So the laws of exponents aren't like laws of a government that somebody decided and made up, this is how we want it to work. It is more like the law of gravity. Once we have defined exponents, then the laws say this is how they work of themselves. So you can't just kind of pick and choose and make up how you want them to behave. You have to learn how they behave. So looking at this definition, so A to the N, so A to the 1 is just A. A to the 2 is A times A. A to the 3 is A times A times A. So looking at that pattern, one thing to note is, what if I want to kind of go back from A cubed, let's say, and I want to go back to A squared, which is A times A. Well, I'm subtracting 1 from the power, and what I'm doing is I am dividing. So going from A times A times A to just A times A, I've divided out and kind of canceled out one of those A's. So subtracting 1 from the power has the effect of dividing by A. And you have the same thing going from A squared to just A to the 1. So if I follow that pattern, then dividing A by another A equals 1, but that would be A to the 1 minus 1, which would be A to the 0. Now, I can't do that if A is 0. We really pretty much aren't going to ever have a base 0 because it would just be 0 the whole time. But if A isn't 0, then the pattern says A to the 0 is 1. So we can think of kind of a number line here where we have the powers of A going on, where 1 is like the A to the 0, and then we have A times A. So like if it was 2 to the 0, we would have 1, and then 2 for 2 to the 1, 2 squared would be 4, 2 cubed would be 8, 2 to the 4th would be 16. So instead of counting by adding that value repeatedly, we're counting by multiplying that value repeatedly. What happens then if we follow this pattern on from A to the 0 and go, what about -1? We have 0, 1, 2 to the right, 0, then -1, -2, etc. to the left. Well, if we continue subtracting 1 from the power is dividing by the base, we would then have 1 divided by A. And then we would have 1 divided by A divided by another A, which would be 1 divided by A squared, 1 divided by A cubed. So a negative power means it's that base to the positive of that power on the bottom. So A to the negative N here equals 1 over A to the positive of that power. Note also then, if I have 1 over A to the negative N, Well, a to the negative n is 1 over a to the positive n. But that is just using fraction rules. That's 1 times the reciprocal. So 1 times a to the n over 1. And that's just a to the n back. Or another way to look at that is this is a to the negative n to the negative 1 power, because it's on the bottom. So going in reverse from the 1 over a to the power is a to the negative of that power. So actually backing up, this in reverse would say this is a to the negative n, which is a to the n. But it is also a to the negative n to the negative 1. So that goes more with another rule, though. What happens when we multiply different powers of the same base? Well, if I have a to the m, that's a times itself m times. And then a to the n is a times itself n times. And so if I have m a's being multiplied together, and then another n being multiplied together, how many total a's are being multiplied together? Well, I just add m plus n. So multiplication of the whole exponential expressions has the result of adding the powers. Similarly, division has the result of subtracting the powers. So we can also think of this as, so this is a to the m times 1 over a to the n. The negative power rule going from left side to right side says that's a to the m times a to the negative n. And then the product rule says that's a to the m plus negative n, which is a to the m minus n. But also, that would be, so that's a to the m minus n, but m minus n can also be thought of as it's the opposite of if you subtracted n minus m. So that would be then 1 over a to the n minus m. This form is more convenient to use if n is bigger than m. So like if I had x squared over x to the 5th, rather than taking x to the 2 minus 5 and getting x to the negative 3, and then rewriting that as 1 over x cubed, I can just go straight to 1 over x to the 5 minus 2 and just get there a little bit quicker. But you'll often have with exponents, you're getting from point A to point B, but it's like many Indiana streets, at least, or anywhere where you have fairly flat ground, you have like a grid of streets. So you might get from point A to point B by doing something like this, or maybe you do this first and then that, or maybe you break it down into more smaller steps and do something like this. Maybe you even go really roundabout and you go over here and then down and then back and kind of go in circles. The important thing is that you stay on those roads. You cannot just go straight. You can't just go, somewhere off the roads. You have to stay. So in the context, then you have to stick with these rules, but the order that you do the rules and how you break it down, there's lots of variation on that. All right. The next rule then, a to the m to the n. Well, that's a to the m times a to the m times a to the m n times, but the product rule says that's then going to be a to the m, and we're adding the m n times. And when you add something n times, that's the same as taking that thing times n. So we get a to the m times n. And then we have the power of a product. Again, the definition of exponent says that's AB times AB times AB, that multiplication n times. But the way multiplication works, it can be reordered freely. So I can just group all the A's together, and that's n A's being multiplied together, and then n B's being multiplied together. So A to the n times B to the n. Similarly with division with fractions, this is A over B times A over B, however many n times, but multiplying fractions, you multiply the denominators and you multiply the numerators. They're each getting multiplied n times. Right, so those are the laws. We're just going to look at a few examples of using these. So 1/5 to the -2 power. A couple different ways I can approach this. One is if I go ahead and think of this as 1/5 to the -1 squared. So using all of these rules can be used either from left to right or from right to left. So this is using the power rule in reverse. Then I can apply the negative power and say, well, that means it's 5 squared, and that's 25. Or I can say, well, the -2 power means that this is 1 over 1/5 squared. And that's 1 over 1 squared over 25 squared, 1 over 1/25, but that's 25. I could take this as, I could apply the -2, so it's 1 to the -2 over 25 to the -2, but then I could say, well, the 5 to the -2. But then I can say, well, the negative power just means if it's on the bottom, it goes to the top, and if it's the top, it goes to the bottom. So that's 5 squared over 1 squared, and that's 25. Again, various ways I can get there. The negative flips it, the 2 squares, the 1 and the 5, but squaring of the 1 doesn't really do anything significant. 2x cubed squared, the thing to know there is the 2 is getting squared and the x cubed is getting squared. So this is 2 squared times x cubed squared. The square, again, and that means it's 2x cubed times another 2x cubed is another way to look at it. But so that's going to be 4 times x to the 3 times 2, or 4x to the 6th. Or I can think of this is 2 times 2 times x cubed, but that's 4 times x to the 3 plus 3, still gets to the 4x to the 6th. All right, next example, x to the -3 times x to the 5th, just using the product rule, that's x to the -3 plus 5, which is x squared. Then 2/3 to the 4th power, applying the power of a quotient rule, that's 2 to the 4th over 3 to the 4th, which is 16 over 81. And then 2x to the 4th over x cubed. When you have different bases, so like a number is kind of its own base, and then any individual variable is its own base. So the 2 is just the 2. The x to the 4th over x cubed is x to the 4 minus 3. So that's 2x to the 1, or just 2x. 4x cubed over x, you can think of that's 4 over 2 times x to the 3 minus 1, because that unwritten power is a power of 1. So that's 2x squared. So that type of simplification. And then we have e to the x squared times 1 over e squared. So e to the x squared is not the same thing as the square of e to the x. Here we have x squared is the power of e, whereas the square of e to the x would be simplified to e to the 2x. So this cannot be simplified in any way or changed really to anything else. But we can combine it with this other thing. So this is e to the x squared times e to the -2 is one way to look at it. And then I can add those powers. So this is e to the whole power now is x squared minus 2. I could also get there if I look at this, well, e to the x squared times 1 over e squared is e to the x squared over e squared. And that's then using the quotient rule, e to the x squared minus 2. So again, different paths to get to the same result as long as you follow the rules. Don't try to apply them where they don't apply. That's the laws of exponents.